Okay, so this next section, what we're going to be doing is still looking at limits, but we don't really want to have to graph them every time. So what we want to be able to do is just to evaluate limits algebraically. So we're going to evaluate limits algebraically. Now I told you before, you can always evaluate limits graphically. So if you're more comfortable doing that, you can, just this is going to be a more precise way to do it. So what our goal is to take limits that are of an indeterminate form, and find an equal limit that's easy to evaluate. So that's our goal. We're going to have different limits. They're going to be indeterminate, and we'll talk about what indeterminate means, but we're not going to be able to plug in like we were with continuity stuff. So what we're going to do is take that limit, rearrange it, and then plug in our number. So one thing we need to recall is that if f of x is continuous at x equals c, then the limit as x approached c of f of x was just f of c. So if my function was continuous at a number, I could just plug it in for the limit. So we're going to use this over and over again. Now, what happens if we can't plug in? Do we have to look at the graph? That's the question. I mean, this is the easiest way to evaluate a limit, is to say if it's continuous, just go ahead and plug in the c. But what happens if it's not continuous? Well, if it's of an indeterminate form, then we can rearrange it. So what are the indeterminate forms? Indeterminate. Well, there are a lot of them. We'll talk about 3 of them. You could have 0 over 0, infinity over infinity, and this is plus or minus. Infinity minus infinity, infinity times 0. There are a ton more. These first 3 are the ones that we'll look at for examples. What this means is that when I have a limit and I plug in my value c, if I get something like 0 over 0, that's an indeterminate form. If I get something like infinity over infinity, that's indeterminate. If I plug in my c and get infinity minus infinity, that's indeterminate. So if I have these indeterminate forms, I can look at one of the 4 ways that we're going to go through to evaluate the limit. So again, what our goal here is to take a limit that's indeterminate, meaning I can't just plug in my c value, and I'm going to do something algebraically to it so that I get a different function where I can just plug in. So there are 4 ways that we're going to do this. First way is factoring. Factoring typically is going to be dealing with polynomials. So for our example, let's look at f of x is x squared minus 4 over x minus 2, and I want to know what's the limit as x approaches 2 of f of x. Now if this was continuous at x equals 2, I could just plug it in. But what happens when I plug in 2? So when we plug in 2 into f of x, what do I get? F of 2 is 4 minus 4 over 2 minus 2, which is 0 over 0. This is an indeterminate form. So that's what we were talking about with indeterminate forms. It means when I plug in my value, I get something like 0 over 0. So whenever I have an indeterminate form like this, I could try something like factoring. So here's what I could do. X squared minus 4 over x minus 2. I got 0 over 0, so I bet x minus 2 factors out of both of these. So I get x minus 2 on the bottom. The top one factors as x minus 2 times x plus 2. And now these are going to cancel, so I just get x plus 2. But you want to be careful. These 2 things are only equal for x not equal to 2. Because I can't plug in 2 to the left-hand side. So these are only true for x not equal to 2. But it's okay in the limit form. Limits, we're not talking about function values, we're talking about the limit of a function. So doing this factoring tells us that the limit as x approaches 2 of my function, x squared minus 4 over x minus 2, is the same as the limit as x approaches 2 of x plus 2. Because I got that these two functions are the same for everywhere except for 2, meaning everywhere close to 2 these are exactly the same, I can say their limits are the same. And now is this a function I can just plug 2 into? Yes, so I get 2 plus 2, which is 4. So I started with a function here that I couldn't just plug 2 into. So what did I do? I rearranged it by factoring, got a function that was equal to it everywhere except for this point, but that's okay because in the limit we're not talking about particularly at that point, we won't really close by. Plugged in 2 to my new function and got 4. So that's the first way you can do this. Generally with polynomials, when you get the form 0 over 0, you can factor. So first way to do it is factoring. Second thing we're going to look at is canceling. Similar to factoring, but not quite. In this example, let's look at f of x is cotangent of x over cosecant of x. And I want to know what's the limit as x approaches pi of f of x. Well, let's see. What happens if we look at the limit as x approaches pi of cotangent and we look at the limit as x approaches pi of cosecant? So let's look at those two. So we have these two limits. Now you can look at your calculator for this. The limit as x approaches pi of cotangent, remember cotangent is 1 over tangent, so in your calculator you would type in 1 over tangent. And then we're looking at the limit as x approaches pi of cosecant, remember that's 1 over sine, so in your calculator you would type 1 over sine. If you actually look at these limits on your calculator, you'll get infinity over infinity. So that's an indeterminate form, meaning that I can't just plug in my value pi. What I'm going to have to do is do something else. I mean, I could look at the graph, but let's do this algebraically. So currently, I have that f of x is cotangent of x over cosecant of x. Now, what was cotangent? Cotangent, remember that's 1 over tangent, or you could think of it as cosine over sine. And cosecant was 1 over sine. Now I'm going to rewrite this top part a little bit. I'm going to bring out that cosine. So the numerator was cosine x times 1 over sine x, and then on the bottom 1 over sine x. Now these two terms are going to cancel. So this is equal to cosine of x. Now again, these two things are not equal at x equals pi. So this is for x not equal to pi. Because I couldn't plug in pi to this original one, so therefore I should not be able to plug in pi here. But it's okay in the limit form because the limit doesn't have to be the function value. So what this tells us is that the limit as x approaches pi of cotangent x divided by cosecant x is the same as the limit as x approaches pi of cosine x. Now what is the limit as x approaches pi of cosine x? I could just plug in pi here, so we'll get cosine of pi, and go to your unit circle for this. What is cosine of pi? You get -1. So by taking my original function, that was an indeterminate form, infinity over infinity, I was able to cancel, say that this is equivalent to cosine of x in the limits, and then I could plug in pi and get -1. Okay, so that's the second way that we're going to do algebraic limits. Number 3 is going to be the conjugate. So I think it's probably a good start to remind you what a conjugate is. The conjugate of a plus b is a minus b. So that's what the conjugate is. It just says take the second one and make it negative. These are really, using the conjugate is really good for radicals. So I'll put a star. This is used a lot for radicals. So remember, Factoring was used a lot for polynomials, whenever I had 0 over 0. Canceling usually uses for trig. We'll use that a lot for trig. And then the conjugate will be used for radicals. So let me give you an example of what I'm talking about here. Let's say that f of x is x minus 9 over the square root of x minus 3. And I want to know what's the limit as x approaches 9 of f of x. So intuitively, what we want to do is say, can I plug in 9? Well, what happens when I plug in 9? Well, let's see. Plug in 9 for f of x. In the top, I'll get 9 minus 9. In the bottom, I'll get 3 minus 3, which is 0 over 0. This is an indeterminate form. Now, these are kind of polynomials. I mean, this one's not a polynomial. This is because of the square root here, but you want to factor. I know that's the initial kind of idea, is to factor, but how are you going to factor when I have a square root of x? So this is where the conjugate comes in. What I'm going to do is multiply by the conjugate of the part with the radical. So I'm going to multiply by the conjugate of the radical part. So my radical part is the denominator, but I can't just multiply anything by a different number, so I got to multiply by 1. So I'll take x minus 9 over square root of x minus 3, and then I'm going to multiply by the conjugate. The reason I do this is because I'm multiplying by 1. Anytime I do the square root of x plus 3 over the square root of x plus 3, this is just 1. So I can multiply anything by 1 and get the same thing. So now what happens? Let's look at my numerator. So I'll FOIL this out. So I'll get x times the square root of x. Well, what is that? Well, actually, let's not FOIL it out for now. We'll worry about that later. So I get x minus 9 times the square root of x plus 3. We'll worry about it if we have to FOIL it out later. What about the bottom part here? So I'll get the square root of x times the square root of x. Well, that's just x. Then I'll get plus 3 times the square root of x minus 3 times the square root of x minus 9. Well, this plus 3 root x minus 3 root x, those are going to go away. So I get x minus 9 over square root of x plus 3 over x minus 9. Now you can see why I did not FOIL out the top. I wanted to wait to see if we had to, because my x minus 9s are going to cancel. So I get the square root of x plus 3. So what this tells me is that not necessarily at 9, because I couldn't plug in 9 to my original problem, but f of x and square root of 3 or square root of x plus 3 are the same everywhere except for x equals 9. So these are equal functions except for where x is 9, because I couldn't plug in 9 to my original function. How does that help us? That tells me that the limit as x approaches 9 of my function, x minus 9 over square root of x plus minus 3, is the same as the limit as x approaches 9 of the square root of x plus 3. And now what is this? Well, I can plug in 9 to that. So I'll get the square root of 9 plus 3, which is 6. So by multiplying by the conjugate of the bottom, or with the conjugate over itself, because you can only multiply by 1, you can't change the problem, I was able to find an equal limit where I could just plug in 9. Alright, the last way that we're going to look at algebraically doing limits is combining fractions. So an example of this would be something like the limit as x approaches 3 of 1 over x minus 3 minus 6 over x squared minus 9. So here my f of x is 1 over x minus 3, and then my, minus 6 over x squared minus 9. So I want to know, what is this limit? So first ask yourself, can I just plug in 3? So what happens when I plug in 3? Well, what's the limit as x approaches 3 of 1 over x minus 3. Depends on if you're looking at the left or right hand side, but it's either plus or minus infinity on either side of it. And what about the limit as x approaches 3 of 6 over x squared minus 9? If you look at the graph, that's going to be plus or minus infinity, depending on if you're looking at the left or right hand side. So the form of this limit is infinity minus infinity, which we already talked about. That's an indeterminate form. So whenever I have fractions like this, and I can't just plug in 3, if I try to plug in 3, I'll get 1 over 0 and then 6 over 0, so I can't just do that. What we're going to do is combine the fractions. So I'm going to combine my two fractions. So let's see what I get here. I need a common denominator, so maybe I'll try to factor this second fraction first. So x squared minus 9, that's x minus 3 times x plus 3. So if I'm going to find a common denominator, I'll say, oh, this denominator doesn't have a factor of x plus 3. So I'll multiply the whole thing by x plus 3 over x plus 3. And then this one will still be 6 over x minus 3, x plus 3. Now combine these, so I'll get x plus 3 minus 6 over x minus 3, x plus 3. Let's see here. X plus 3 minus 6 is x minus 3 over x minus 3 times x plus 3. My x minus 3's are going to cancel, so I'm just left with 1 over x plus 3. So I combined these two fractions by finding a common denominator. Once I combined them, I got 1 over x plus 3. Now how does that help us with the limit? This tells me that the limit as x approaches 3 of my original function, which was 1 over x minus 3 minus 6 over x squared minus 9, is equal to the limit of the function I just found, which was 1 over x plus 3. Now, is this a function that I can just plug in 3 to? Definitely. So I'll get 1 over 3 plus 3, which is 1/6. So by combining those two fractions, I was able to just plug in 3. So whenever you have two fractions like that, a good way to try it is to just combine them and see what you get. The last question to ask is, what happens if none of these work? So what do you do if this doesn't work? Well, then you go back to the limits you were doing before and use your graph or the table. So, for example, let's look at the limit as x approaches 1 of x squared plus 4x minus 2 over x minus 1. Now, I definitely can't plug in 1, because if I plug in 1, I'll get 0 on the bottom. But what's the form of this limit? If I plug in 1 to the top, I'll get 1 squared plus 4 times 1 minus 2 over 0. Well, let's see, that's 5, so I get 3 over 0. That's not an indeterminate form. That's not 0 over 0, so we can't really use factoring. You can only use the factoring when I have 0 over 0. So what do? I look at the graph. So if you graph this, it has a vertical asymptote at x equals 1. And then it kind of does this, like that. So what is this limit? Let me move this up just a little bit here. Well, let's look at the right-handed limit. So one from the right of my function, and then let's look at it from the left. So look at my graph. Here's x equals 1. If I start to the right and go along the curve, what are my y values doing? Well, they're going off towards infinity. Now look to the left. What are my y values doing? They're decreasing, so negative infinity. So what does that mean my limit is? So from this information, we say the limit does not exist, because these two things were not the same. So if you can't do one of these algebraic techniques that we just did, just go back to your graph. Go back to your graph or go back to the table. Those will always work. These algebraic manipulations are just so you can have more of an exact answer instead of guessing from the table or the graph. So if none of them work though, go back to what we were doing. That'll always work.